All right, now let me remind you where we were left at on last Wednesday precisely, and then let's deduce our plan for the rest of the day today. Remember, we are trying to find neoclassical answers to the question of what determines per capita income differences across the globe. That's our objective. And in so doing, we have invoked certain hypotheses from the neoclassical tradition and laid out the groundwork. And when I left with you the last week, dramatically, we were trying to answer the following question. Under the neoclassical world, roughly meaning a neoclassical production function, setting out the relationship between factors, capital and labor, and an exogenous technology to output. There is only one single output and two factors of production, labor growing at its own rate exogenously, and capital is being saved and identically invested. And under this setting, we have the following picture of the world. There are machines, okay, and there are humans. Machines are expanding at the rate of investment, saving and investment, which is common, and also depreciating. So every year, labor grows at the rate n. That means new workers are added. And every year, households save a little s% of output that is directly invested. So we expand the factory by investment, but yet, due to wear and tear, a portion of our capital, existing capital stock, depreciates at the rate delta. New investments, some portion is already depreciated. So the size of the factory expands to a new rate, net of depreciation. And this continues every year. New investment, a portion depreciates. New investment, a portion depreciates, so on and so forth. And this is the end result of saving rate. And this is the end result of population growth rate. The question is, in an economy where machines, capital, expands due to new additional investments subject to depreciation, and population grows at the exogenous rate n, how do we ensure full employment of labor and capital in market equilibrium? In an economy where capital is expanding due to investments and depreciation, and labor is expanding due to an exogenously given population growth rate, what is the mechanism that ensures full employment over the long run of labor and capital in a market setting? How is it that I can ensure full employment equilibrium, not only today, not only tomorrow, not in November, not only in 2019, but for indefinite future, for centuries to hold? We are talking about a long-run equilibrium. So this is the question we are going to tackle. And in that equilibrium, we are going to check whether we can explain per capita income differences across the globe. That's our objective. So what do we do? How do you put the problem in algebraic notation? That is the picture of what's happening. Shut your eyes, capital expanding, labor, little people are being added, and the ratio of machines to the number of people. That's what we are interested in. So algebraically, what is my problem? What do I have to look at in symbols? Great. What's the symbol of this machine? Capital, K, big K. So I am interested in capital divided by workers, labor. This is a crucial ratio in this whole analysis. How much capital do I have per labor? Capital-labor ratio. How much capital does each unit of labor work? And since I am in a setting where this capital is expanding, depreciating, so on and so forth, my question is, how do I get the change in capital-labor ratio over time? How does capital per worker change in this economy? Under the neoclassical assumptions, one neoclassical assumption is investment per labor is equal to savings per worker. And I also know that in this economy, capital changes, that is changing K, or KT plus 1 minus KT. That's the all synonymous notation, in notation-wise, by new investments minus delta K. These are my rules of the game. Investment per labor is little s of a function narrating capital per labor. And capital changes over time. That's the change in capital stock over time, KT plus 1 minus KT. KT plus 1 minus KT. That's the rate of change. Is investments minus depreciation of capital. Now, under these conditions, first of all, I want to check how capital per labor, how does capital per labor change over time? Capital per labor, that's the whole thing, changes. How does it change? Well, let me continue from this side. Change in capital labor ratio. In notation, I am going to denote this as little k. Little k is total capital divided by labor. By notation, we are going to use the smaller letters for per labor units. And now little k is total capital labor, and I'm going to put a dot sign to indicate that I am interested in the change in capital labor ratio. That's the definition. Let me put 3 bars here to indicate that that's my notation. That's an identity. Well, what is it equal to? Well, according to the multiplication rule, it's equal to how much capital changes times the denominator plus changes in L times K all the way divided by what is in the denominator squared. That's the quotient rule. Numerator, change in numerator times denominator plus change in denominator times numerator divided by whatever in the denominator is squared. Well, that turns out to be equal to change in K. This is my change in K. That's the change in capital stock. Investments, net of depreciation. So for change in K, I am writing investment minus delta K times L divided by L squared. These characters drop out. Plus the second term, change in L. I am going to use one of the L's as for L squared times K and the other L. So rather than L squared over here, I have used it L times L, and that's my change in L times K. What am I left with? So this is K dot turns out to be equal to investment over L here minus delta K over L plus delta L over L, that's the growth rate of the population of the economy. N. Buyurun. Which one is minus?
Because it's division.
Pardon, şurası. Tabii. This one, right? Sorry. Thanks for correction. Definitely. I'm talking about division. Definitely. So, minus N. That's the change in L over L. And this is little k. So K dot is investment over L. And now you are introducing a very strong assumption. It is not it's simple, but a very strong assumption. Investment per labor, this economy is savings per labor, and savings is equal to saving rate times output per labor. Output per labor is a production function telling us, tell me capital labor ratio along this little f production function. I am going to tell you how much output is produced. So f of k is per capita income. That is output per labor. S times output per labor is savings per labor. And by making this equality, I am invoking the neoclassical assumption that in this economy, whatever saved is automatically invested. And whatever saved is saving rate times output per labor in functional form. Minus delta, k over L is little k, so I am just putting delta plus n k. Like in this algebra, up until now, remember from last week, we have made our life easier by assuming that technology changes in this economy in a manner that I cannot tell, and I don't want to deal with characters in this model that I do not know how they behave, so I tend to forget them away. And when I do that, I am going to assume that there is no technical change, everything is same. You can put any number over here, 1%, 10%, hani ağın eli tutulmaz, 100%. It doesn't mean anything. What it will do is only increase output per labor by X%. But that's something I cannot explain. Why does technological change occur? I am taking it exogenously. And if I am taking it exogenously, better I forget it away. So I am not going to carry out any additional variable, just mixing my notation. Same is here. Labor force grows at the rate n. Rather than adding something that I do not explain or take it as exogenously, I will just make my life easier. I will simply assume population growth away. This is unrealistic, I agree, but our concern is trying to understand per capita income differences from the variables that I can tell. If I am making my analysis on something I cannot find the reason for, then there is no reason for doing this analysis. So X and labor growth, L dot over L, are exogenous things that I am going to simply, for the time being, put aside. We are going to analyze non-zero, non-exogenous, that is endogenous sources of technological change due to the now rookie Nobel laureate, Paul Romer, and his gang, and Rutherford. You mentioned something? Nordhaus. Nordhaus is mostly on climate, but he's also a general equilibrium modeler. But Romer is mostly interested in precisely this. Until then, I'm just going to assume them away. So this n goes out. What am I left with? I am left with this equation. K dot. What is K dot in plain words? Not growth rate. It is change in. If I divide it by K, then I have growth rate. Change in capital per labor. Machines per workers is equal to, according to my notation, S times f of k minus, since I assumed n away, times delta k. One of the most famous equations of our profession, the Solo's adjustment mechanism. This is how an economy under market conditions and under neoclassical hypothesis, but let's leave this aside for a moment. How does capital per labor change over time? It changes over time, S times f of k minus delta k. It's like a mythological setting. One of the most powerful equations, how does long-run capital per labor change under neoclassical conditions? What does it say? Change in capital labor ratio is equal to, yes, savings. Okay, investment.
Investment of capital.
But be precise, investment, since this is output per labor, this is investment per labor. So capital per labor changes, machines per worker change over time by investment per labor minus depreciation of capital per labor. Is this something you don't know? Here it is. Capital labor ratio, the ratio of machines to number of people, change over time. How? Two things. I assumed away these characters. Two things. How much do you invest? I have invested this much. This is investment per labor. Right? So I have, all right, let me continue from this equation. So erases the question mark. Capital per labor changes by the additions, that's my I over L. Okay? In a neoclassical setting, S times f of k. But what it is saying is actually, how much did you add to your capital stock per person. The new green picture of the machines that I have added. Then what? Well, due to sunshine, wind, harsh winter conditions, so on and so forth, a portion of my capital stock, alas, depreciated. Well, what's its size? Well, there is some delta here telling me that delta K of my machines are deteriorating. Okay, it drops out. So this is my new capital per labor. That's what it's saying. Investment per labor, how much did you add to your capital, minus depreciation of your existing capital per labor. If you have more investment than depreciation, that is, if S times F of K is greater than delta K, if this is true, then the implication is K dot is positive. Definitely.
So do we have profit now?
Right now, we haven't entered factor prices into the analysis. We are simply setting out the adjustment rule of capital per labor. The adjustment rule says it's the difference between investment per labor and depreciation. And all I'm trying to say is that this is a very big, very useful formula from Solow analysis. But it's a very simple notation. It is telling me something that I already know. There was no need to scratch out this algebra. This is only for putting us into some notational discipline. But what it is narrating is, if investment is greater than depreciation, that is, if the size of capital that I have invested exceeds the size of the capital that is being depreciated, of course, capital per labor increases. So if investment is greater than delta K, we have capital per labor increasing. Well, yes, by tautology. Otherwise, if the other is true, if you invest less than the amount of depreciation, then K dot, that is the change of capital per labor, is decreasing. Buyurun.
Is there a technical problem in saying per capita instead of per labor?
No, but in this analysis, every human being, if that capita, per capita, is to be recognized, it has to function as either worker or capital owner. There is no difference between households and workers. All households, that means all labor works, all labor is also workers. So when we mean per capita, we don't include you. You are not part of the labor force. We don't include your grandmothers, grandfathers who are retired. They have completed their job in the economy. You haven't started yet. Hopefully you will be in the labor force with some employment, contributing hopefully some marginal product in a positive way. The reverse happens, you know, that's you enter your job place, then you start asking silly questions, you hold, you question the authorities, whatever the established system, you bring negative energy for change, and then your marginal product ends up negative. We call this creative destruction, and we are going to see that it's actually, in the long run, it is helpful and useful, but it has cost in the short run. So there is no difference between, in notation, per worker, per labor, or per capita. All right. Now let's then draw this in a useful fashion, something that you are already familiar. But now let's bring in profits into the picture. Here is what's happening. We have little k and per capita income, that is per capita output, which is a function, a neoclassical function of capital per labor. And we invoke the hypothesis that GDP is a function of capital and labor. A is treated constant and assumed away. And this is constant returns to scale. That is, increase capital and labor by some lambda, and output increases by that lambda. That is the meaning of constant returns to scale. If this capital F function is constant returns to scale, that is, if F is constant returns to scale, then, see, there's a sufficient condition. If then it is sufficient to know that. There's a sufficient condition. Then output per labor function is a function of the capital labor ratio. This is not always true. This is only true if my production function, the underlying production function, is of constant returns to scale. And you have proved this for today. If you have any ambiguities, any non-clear dust in your memory or in your expertise on this, on Thursday, Gökberk will go over it. But this is a very important relationship. But what about F? F is diminishing returns in K. That is, holding labor constant, increases in capital, that is, increased capital per labor. Increasing capital without changing labor. That is in diminishing returns. Constant returns in scale, diminishing returns in capital per labor. So if it is diminishing returns for capital per labor, then I have a concave function of this sort. That is y is equal to f of k function. I draw this as a concave function, as a hyperbola, as a belly. Why am I drawing this in this fashion? Simple answer. I assumed so. I assumed that the production function is of diminishing returns to capital. And the power of that assumption now follows. Then you know part of this deity. If my production function is this one, and I am saving s times f of k. That's my saving function. And there is also a depreciation rate, something of the sort. That's a depreciation rate, delta k, that should be a straight line, which narrates this equation. And the difference between the two is the change in capital. So k dot is s times f of k minus delta k. That is investment minus depreciation. And this is my S times f of k function. The difference between this ray and the S times f of k tells me that capital increases in that region. So it increases over time, and when this thing happens, then there is no change. What does it mean, this is being equal? It means investment per labor is equal to depreciation of capital per labor. So you are simply adding new investment to replenish the amount of depreciation. So there is no further increase in machines. There is no deterioration. So if this is true, then trivially, k that is 0. So this economy goes all the way to the equality of the saving function with the depreciation ray, and at this rate, the economy stops increasing capital per labor. And this is called the steady state value or the critical value of capital labor ratio. Once we achieve there, we stop there. We have reached long run equilibrium. And how do I go there? All in this region between the times of Adam and Eve, where they had only one apple as their endowed capital, and they ate it, and that's why they are kicked out of the heavens. But from the biblical times, where you had very little capital, perhaps a tiny bit of a nail or something that could have been used as capital. But then you have added investments, and investments followed this function where all investments were in excess of new depreciation until we reached the steady state value of capital. How do we go there? Well, mechanically, we go there because according to the functions, S times f of k is higher than lambda k. Therefore, k dot is positive. Does everyone agree? Does this satisfy you as an answer? But why? How? What is the mechanism that brings this algebra more realistic life? Now let's see what the people are doing. Before then, any questions on the definitions, notation? Let me erase this. I want to use this part. How do people behave in this economy? Well, each factor is paid its marginal product. Capital owners, their contribution is f prime, that is the first derivative of the production function, which in economics we call marginal product of capital per labor. That is change in output due to changes in capital per labor. Marginal product of capital in equilibrium is equal to the profit rate or the cost of capital. And in this economy, profit rate is written inclusive of depreciation. We are talking about the gross profit rate. because capital depreciates and you are paying something to recover that depreciation by your investments. So R is net profit rate that is being pocketed. R plus delta is gross profit rate. Total returns to all capital. A portion of it disappears, but you have to pay for it. It's like gross domestic product versus net domestic product. So F prime is R plus delta. That's how capitalists work. How do you show F prime in this picture? Well, this is my production function over here. And using this amount of K, this is the amount I am producing. To approximate for the derivative of this production function, what we do is we put a tangency here, call this tangency F prime. The tangent of this production function, the slope of that ray, is what I call derivative. That is, given an infinitely small change, which is approximated by the slope of the ray that is tangent to the production function at that point. You remember this from your calculus classes, perhaps from your intermediate high school algebra. But anyway, believe me, this is true. So this, let me call this point A. And there is this tangency line. Let me extend this all the way. It hits the axis. Let me call this point B. And there is an angle here. Let me use little a for angle. Thus, the tangent at alpha is approximated by the opposite side, the distance by star, that's the distance, divided by the distance ay star. Çok yaşayın. And this tangency, now I'm using economics, is equal to F prime, valued at this K star, is equal to R plus delta. This is mathematics. This is neoclassical economics. Mathematics say that give me a function. I don't care what you call that function, production function, consumption function, whatever you name it, I do not care. Give me a function. If you want to measure the derivative of that function at point A, or using this amount of the variable K, the derivative is opposite side divided by adjacent side. And this derivative in economics is the gross profit rate. Gross profit rate. Okay. The distance by star then is equal to F prime, which is R plus delta, times the distance ay star. Now, what is this distance? This is the amount of capital that I am using. It is K star at steady state. Capital times profit rate. Profit rate per capital times capital. So this whole sum, profit rate times capital, is total profits per labor. So this equation tells me that this is profits per worker. Then what is this distance? The distance, this is total output. Depreciation of capital is given by this ray. So this much is depreciation of capital per labor. That's the delta K. This is how much K you are using. So this is total depreciation. It is also equal to S times F of K, remember. So it is equal to investment per labor. But this is a good story to keep in mind as well. So this is depreciation of K, or let me write in small hands, of capital per labor, which is equal to also S times F of K. So it is also equal to investment per labor as well. And since they are equal to each other, there is no change in capital. And this is how much we produce in total. If this portion is equal to investment per labor, what is this portion equal to? What should happen to it? You are producing this much. This is investment. The rest, net. It's equal to consumption per worker, consumption per labor. So this portion is my C over L. Consumption plus investment is equal to total output. There is no government, there are no X minus imports. So investment equals depreciation plus consumption. This is the total value of output from the expenditure side. Now I am coming to value of output from income side. This is share of capital, profits per labor. So what's the remaining part? Wage costs, right? Per labor, or the wage rate. How can you write it? Total output minus R plus delta, little k, value of output minus profits should be equal to wages per labor. This is profits per labor. And this is output per labor. Output per labor, Y, minus profits per labor is equal to cost of labor, wages per worker. Wages per worker means the wage rate. Just like total profits per capital is profit rate. And I use the symbol W for it. So W is output per labor minus profits per labor. Can you write me what is output per labor in functional terms in algebra? What's the symbol that I'm using? No. Output per labor. y over L, or in terms of functions, that is little y, f of k, right? That's what we mean by output per labor. Either you use little y or y over L. That is, let's use wage rate, okay, W, wage rate, wages per worker. Hanginiz maaş alıyor burada? Emre Bey. Bir 50 bin lira alıyorsunuz herhalde. Burası zengin bir üniversite. Evet, ayda 50 bin lira Emre Bey'in. Anyway, so wage rate of Emre is X thousand liras. Wage rate of. The total cost of wages at Bilkent is perhaps 100 million liras. I don't know. It is wage rate times the number of Emres and us working for Bilkent University. Wage per person, wage rate, is equal to output per labor, which is f of k, minus profits per labor, r plus delta times k. For r plus delta, I can rewrite f prime, right? That's what r plus delta is, f prime. Is everyone here? Okay. All right, so f prime and times, there is a k here, times k. So wage rate is output minus profits. F of k minus f prime times k. Do you remember this expression? From where? Bravo. Bravo. Voila. You probably did something in algebra, have taken derivatives and so on and so forth. But it's tautology, it's by definition. Output minus profits is equal to wage rate. Output minus wages is equal to profits. Wages plus profits is equal to output. Hani diyoruz ya, economics is a simple game, like football. But it's hard to play economics simple, that's the root one thing. It's a very simple notation. If this part is profits and this part is the wage rate or wages per labor. So from this picture, I can tell you that if your economy has not reached to the long run equilibrium yet, somewhere around here. Let's say this is my K0. That's initially, or K 2018. Let's use that one, it's more fun. 2018. And looking at these pictures are narrated. Suppose that this is the how much I am producing now. This is the amount of depreciation. This is the amount of investment. So investment exceeds depreciation. So that means capital is increasing over time. Okay? This will continue to increase because investment is higher than capital. And I go up. This is the amount of production I produce. This is Y star in 2018. Per capita, roughly $10,000 in Turkey. This is where we are. Why is it that investment exceeds depreciation? Okay, I can see here, the way I have drawn these graphs, investment is higher than depreciation. Why?
Maybe because what you invest today will be shown up in the future.
Definitely, sure. That is, if I invest today, capital will move out, then I will have more output. Invest more, output will increase. Invest more, output will increase. If we invest further, output increases, but the amount of depreciation of a lot of capital. I suppose that, hey, this is great. I invest, I increase output. Suppose you've gone all the way over here. This is how much you produce. This is how much you invest. And this is how much your capital depreciates. The capital depreciates even more. Therefore, you come back in this region. So it's not a very clever thing. You are like you are building pyramids and they are just depreciating away and they do not provide any food. But the interesting part is this one. Starting from where we are today, trivially, I just put it at our place. We are not at our steady state yet. Therefore, more investments than depreciation. Capital starts to increase. I can understand that. But why is this distance? Why is it that, let me write it plainly here. At K 2018, I know that K dot is positive. No doubt about this. According to the picture, S times F of K is higher than delta K, This is not economics. This is fine arts, some ugly graphic in growth theories. Now let's be an economist. Why? The question is, why at K 2018 investment per labor exceeds delta K as of 2018? Why is it? Do not concentrate on the picture. Just think economically. Very simple logic. Very simple rationale. Why should you invest? By investing, you mean not consuming. You are throwing away seeds as corn. You are saving, and therefore you are not consuming. Consuming is tempting. It brings utility immediately. If you invest, you produce more tomorrow, and by producing more tomorrow, you are going to be able to consume more tomorrow. That I understand. But why do you invest today? Not increasing returns, but diminishing returns. Let's just backtrack. By not consuming and saving an investment decision, you make yourself a capital owner, a capitalist. Why do you care for? As a capitalist.
I would say that to be better off in the future, you don't consume today.
Tamam, these are very honorable answers. But I want you to think of as a capitalist, as a vulture. You are tasting blood, profits. That's what capitalist is after. You produce more. I am making community service. I am employing these people under the flag. I am the banner. I am this. All honorable. But the bottom line, you have tasted for the profit rate. If profits are high, then you save and invest. Herkes haddini bilecek yazıyor ya stadlar. Yani capitalist will have to act as a capitalist, not as expanding the consumption. So my citizens will consume more, and that's all fine. But as a capitalist, investment is still high, meaning that higher than its long-run steady-state equilibrium, because it must be the case that there is let's say, taste of profits out there. That is profits, gross profits, R plus delta is big or large. Large with respect to what? Large with respect to what will happen under the steady state. Until the steady state, you just continue investing more than depreciating. That is, you want to make your capital stock bigger and bigger. We agree that if you continue this, at this point, it is alas. You will, at every round of investment, you will come back because the depreciation will always be higher than investment rate. Capital stock will shrink. Well, what is R plus delta? What's the profit rate here? How do I find it? What is the profit rate, okay, that I have tasted for at this point? What's the profit rate? How do I find this? The same exercise, isn't it? I did this for this rate, all drawing this tangencies, I repeat the same example. So starting from 2018, you go all the way up to the production function. Let me change colors. And this is the the ray, just like f prime. This is f prime in 2018. And then I extend this all the way here. I call this a new B, 2018. This is output in 2018. Repeat this whole exercise. I don't want to mess my messier picture. I was a terrible art student when I was in high school. I admit my mom used to do most of my homework so that I could just study mathematics and physics, which I hated. But anyway, so you can do this as many times as you want. What is important here is the slope of this ray. The slope of this ray is what I call f prime. And f prime is what I call, in economics, profit rate. How do I find profit rate? I draw a tangency line at that point. The slope of that tangency line is my profit rate. So here, this is the profit rate. Under the steady state, this is the profit rate. Which one is bigger? This is steeper, therefore this has a higher slope. And if you continue, the slope diminishes because I have diminishing returns to capital. But yet, it has not diminished sufficiently. It is still higher than what it ought to be under the steady state. We are going to see how much it will, mathematically, how much it will be under the steady state. But çok yaşayın. At any capital value less than the steady state, because of my assumption of diminishing returns, because of my assumption of this curvature, at each round, the slope diminishes and diminishes, but at each round, it is still higher than what it has to be. This is the neoclassical economics. So here, the profit rate that is happening in 2018 is larger than the profit rate that will prevail under steady state. You can calculate at the expense of making this picture messier. This will be the total profits. The rest will be total wages. Then you continue a little bit. The slope diminishes. The profit rate is reduced. But then it's still high. And you go all the way here because the factor markets telling you that there are profit opportunities out there. Therefore, you have to keep on expanding the size of your capital. That is, you have to invest more than depreciation. Otherwise, yes, if I save today, I am going to consume more tomorrow, all right. But rather than this expectation, the harsh reality today is that, my lad, win big, save, invest, the future is yours. The young entrepreneurial Turkish future generations, invest, because you are going to make profits. Buyurun, hoş geldiniz. So, while we happen working like this, f prime is positive, but is diminishing towards steady state value. Again, any comments on this? Anything? I know that up until now, you have seen this picture saying that between 0 and k, savings is always higher than depreciation. And if you have had population growth rate and x here, that is delta plus n plus x, and seeing that s greater than delta x and whatever, I go towards k star. Now you know why. Why am I investing more? To get profit rate. So if you follow this logic, what do you expect the profit rate to be under the steady state? Net profit rate, R. What do you expect the net profit rate to be under steady state? 0. Why?
Because the profits and the depreciation will be equal to
Right, because I have saved and invested to the extent that if there is any opportunity for net positive profits, then I invest more. I expand my capital. At steady state, the marginal product must be equal to delta. That is, R must be equal to 0. Because if the net profit rate is not 0, then there is always an opportunity for expanding your capital stock. That means you will continue to expand your capital stock, seeing that there is net profit rate. And this profit rate is continuously falling because I have assumed a diminishing returns to capital production function, just at the very outset. Otherwise, this will not work. At the expense of reiterating something, just let me draw this picture more simply once more. If you don't want to take notes, just relax and watch, and then you are going to, I'm going to let you to take account what's on the board. This is what's happening. This is my production function. This is output. This is capital, all per labor. This is my production function, f of k. And then let me use this color. Suppose that this is delta k. Suppose that initially, this is my saving rate. Let's say saving rate, what to solve? Saving rate 1. times f of k. And saving rate and the delta k intersects here. This is how much, this is where I will be at steady state. And this, let's call this steady state 1. And let's call this output 1. This is the long run equilibrium. Now, let's just do this imaginary exercise. Let's save more. What happens if I save more in this economy? If I increase the rate of S1? No, it goes upward. Are you going to save more? So let me just arbitrarily increase this thing. Let's call this S2 times FFK. So what happened? Nothing, everything else constant. Depreciation, shape of the production function. There is no technical change. There is no population growth thing. All of a sudden, I increase my saving rate from S1 to S2. Production function stays as it is. But I have now higher savings. Şurayı tamamlayayım. What do you expect to happen? Buyurun. Our steady state will be higher. So everything will be higher. So let me draw a bigger graph. Old steady state, this is steady state 1 with the old saving rate. I have simply increased the saving function. The production function stays as it is. I'm not changing technology. I'm not adding labor. I'm not adding anything on the production technology. All are exogenous, and I am leaving them as they are. But out of production, I save more for some particular reason. This is my new savings and depreciation. This is steady state 2. So this will be another steady state. Starting from here, tell me please what is happening. All right, compared to K2, the profit rate over here must be higher. Well, so that for some particular reason, I am instructed to increase my saving rate from S1 to S2. The returns to investment seem bigger, and I continue to do so. How about output? How much do I produce now? More, less? This is using this much of capital. I go up, all the way up. This is my production function. So this is my Y2. So per capita output, let's say, goes from $10,000 to, let's say, $15,000. We are a nation that is richer. Is it good or bad? Okay. Y2 is greater than Y1, all right. But what are you doing with more Y2? How much do you consume? Well, this is the production function. Let's highlight our production function. This is the production function. Dot, dot, dot, dot, dot, dot. Before, this is the amount I invest, and this is the amount I consume, right? Now what are the figures? This is my new saving rate here. This is the amount I invest, and this is the whole amount I'm consuming.
Lower welfare.
That's right. If you measure welfare in terms of consumption, yes, you are producing more, but you are consuming less than what it was. So what happens if I increase savings up until some magnitude, you increase consumption, but after that you start decreasing consumption. So there is a trade-off between doing saving or not. If we increase savings, rate of growth increases from K1 to K2. Rate of growth increases, but at a decreasing rate. This we call transitional dynamics. There is a transitional dynamics towards steady state. There are two possible steady states here, and you are free to choose in between them. But in truth, there are millions of steady states. That is, choose S, and it will give you a new steady state. In between, there will be a transition, and that means we'll go towards that transition to the final steady state by choosing the optimal S. This will be our topic on Wednesday. What is my optimal saving rate? This is what we shall do on Wednesday. This is one question. Now there is another question. Going back to independent of the saving rate. When you look at this picture, if you happen to see two countries, one is what we are in 2018, right over here, and suppose that there is another one here, some poor country, again, at 2018. And there are a host of countries, none of which at their steady state yet. Some of them are very close, perhaps like United States, Germany, Japan. There are some people in the middle range, like Turkey, Czech Republic, South Africa, Spain, Greece, etc. And then there are Ethiopia, Nigeria, Sudan, Vietnam, poorer countries, and then real poor countries that's not in the picture yet. If you look at your PWT table, you will see a host of countries over here in per capita income and per capita and capital stock values. What should be true for these poor countries in terms of profitability? They will have more profit opportunities, right? This profit rate will be even steeper. So if you have this sort of a vision of the world, poor countries who do not have enough capital, that's why they are poor, but they will have higher profit rate opportunities. Middle income richer countries have some middle income level capital with less profit opportunities. And there are countries that are rich and close to steady state, and their profit opportunities should be very small. So that means those poor countries will tend to accumulate capital faster, less and less, and the ones that are close to the steady state will have even lesser profit opportunities, and they will grow even at a smaller rate. So from this picture, if you make this as a universal adjustment mechanism of market economies, obeying that profit rate is equal to the marginal product of capital. That's a very, very important assumption. Assuming diminishing returns is not sufficient. Keynesian economics also assume diminishing returns. But you have to add the assumption that marginal product is equal to the gross profit rate. Based on that assumption, today's poor and capital scarce economies will tend to have higher profit rate and will tend to grow faster than today's rich countries, which have abundant capital and they have less profit rate, and therefore they grow at a lower rate. So today's poor nations ought to have higher growth rates, and they will catch up probably with the rest of the rich countries when we reach the world global steady state long-run equilibrium. Everything is harmonious. There is no role for government, no nothing. All you have to do is do not interfere with the market system. Let the market give the proper signals with undistorted efficiency prices, leading to the equality of marginal product to the net profit rate, gross profit rate, and the system will tell you how much to invest, and where to go. Pardon. And this is called, as you probably have worked on zillion times. Pardon bunun için. This is the convergence hypothesis across the world. The poor nations tend to grow faster, and like at the very first lecture I have shown you, if you embrace globalization and obey the market signals, one day everyone will be rich and there will be convergence that the whole world will enjoy. So two issues left or had been understood from this picture. One, this system is driven by the rate of return on capital. That enables the convergence hypothesis. And in the long run, I have to choose the optimal saving rate. And it will depend on the consumption availability. Because hani Karacaoğlan diyor ya, işte insan bu dünyaya niye gelir? At için, namus için, silah için vesaire. We come to this world, Homo economicus lands on this planet to consume. That's what distinguishes Homo economicus from the rest. Capitalists are after making use of this ray, technically, and workers or households or per capita people are after consumption. Any comments? Any questions? Böyle boğazınıza takılan herhangi bir şey that you shouldn't feel. Buyurun.
In this example, the high saving rate country can be say Japan is struggling with this?
Well, we are going to make it clearer on next week. This is when we tend to see data. You see, this picture applies to all countries if all countries have the same saving rate. But if you have different saving rates, then it will tell you that each will go to its own steady state. So if you are comparing two countries over here, one of them has this saving rate, the other one has lower saving rate. It is not easy to make one-to-one comparison as of today, but in the long run, both of them will be at their respective steady states. And if capital is internationally mobile, something we haven't assumed here in this simple, then this excess savings will flow out of that high saving country to low saving countries, because at the respective steady states, they will have still higher opportunities. So even though nations save different rates, the rate of return globally will be the same, because there is one global meta production function. So at the end, even if you save lots or less, we will all go to the zero net profit rate equilibrium. İyi, peki. O zaman çarşambaya görüşüyoruz. Any problem with the homework or anything?